Hey, this is Rick, and I am back with more HTML5 game dev tutorials using TypeScript. I thought I was done with 2D collision detection, but as it turns out, so I was kind of playing around with this asteroids game, and I believe what I said in the previous time I was working on this was that what you could do is when you're working on your game, rather than for some reason get my oh, I know why. I need to get up to layer 7. Duh. So last time, basically what I said was, so if you have asteroids, or something like that, rather than having to do the polygon collision detection, you could do things like, basically a compound collider, like put multiple circles in. But that turned out to be a pain. What I was actually thinking was, for my asteroid detection, so I'd have something like this. And I basically figured, okay, well, I'll just draw, my circle collider, kind of like whatever the closest point was. But then, bullets were kind of going through here and they were going through there. And it didn't look quite like I had hoped. So then I said, okay, well, I'll do a circle collider in the middle, so that it's not too big. And it still didn't work out quite as I had hoped. So basically what I decided to do is a tutorial on polygon collisions using the separated axis theorem, which I had kind of hoped to avoid, but for this little asteroids game, it kind of looked like it was just the easiest thing to do. So I'm going to go through, and basically what the separating axis theorem is say you have two polygons, and we already touched on this with the oriented or rotated rectangles. But let's say you have two polygons like this. The way you could tell if they don't collide is if you could draw a line between them. Okay, that's all that means, so that line between them is called the separating axis. Well, okay, that's easy enough. Well, how do you find what that line is? Well, there will be, if there is any line, there will be a line that is parallel to one of these edges on one of these polygons. So, if you can draw a line, you'll basically have a line somewhere that's parallel to this guy. Let me go a little further. Let me go back to the oriented rectangles, because we've already done a little bit of this. But the oriented rectangles was like a special case, because basically you don't have to do as much testing, because when you're doing your separated axis theorem, like you basically have, what you're trying to do is you're trying to like create a range, along like one of the normals. And this was a very simplistic version, and I just thought when I introduced the oriented rectangles, I discussed projection a little bit, and how projection turns out to be the method by which you can tell if these two collide. And so as I discussed here, you could tell these two edges collide because if you project them, if you draw like kind of this 90-degree angle between the two, between your two vectors, then you could tell if those, like you can use that 90-degree angle to get kind of an overlap along the edge between these two. And if they overlap, that's great, but they have to overlap along every single edge on a polygon. And you could take shortcuts with a rotated rectangle, because basically that this edge is perpendicular to this edge, and if these two edges overlap, then also these two edges will overlap. But anyway, it's a simplified case, and I didn't go into great detail, but I'm going to go into a lot more detail with the polygons, because it kind of like requires it. So, as I said, we have our separating axis theorem, and basically what we're trying to do is determine, if there's any line between here. Now, obviously, there's a line you could draw between this guy and this guy that would go something like that, that there are several lines actually. I mean, there's a whole lot of them, but the one that's important to us, the one that we know has to be there, is basically parallel to this edge. A line parallel to that edge can separate the guys, separate these two polygons. So, getting back to our separating axis, it basically looks like this. It's parallel to this edge, and it goes all the way through. So, how do we find that? Now, the way you have to do it with polygons that we didn't do with oriented rectangles is we have to use normals. And the reason you don't have to do that with oriented rectangles is because the edges of your oriented rectangles are already like normals of each other. So it kind of like is a nice shortcut that you could take with an oriented rectangle, that you basically have to test like half your edges because they're already normal. But if you don't know what a normal is, basically you're creating a vector that's perpendicular to the edge. And then the reason we're doing that is because we want to test, all of these edges along a line. So let me just, I've got this line here. Oh, that's not what I want. What did I just create here? Okay. So I've got this line. Get out of that. This blue line over here. All right. So, when you create a normal, you're basically, testing projections along this normal so that you can, so here's this normal that we want to project along. And we want to say, okay, are there any places where we're not, our projections of all of these edges here are not overlapping, along this normal. And you get that basically by creating 90-degree angles, like along this guy. So, all right. So this is basically roughly, our normal here, and we're going to, take all of these edges. So this edge projects down to here, and we're going to project all of these basically at 90-degree angles, to this line. So this line would extend way out here, and this guy would project there to basically get just ranges, minimum and maximum values along this vector. So, this would be, our min there, and this would be our max here. So we would have this range, and then we'd have to do that for this polygon too, and we'd have to project 90-degree angles. We'd have to project our vectors, creating these 90-degree angles along all these, all these edges. And this guy would continue out here, so our min would be like way down here, and our max would be up here. And if you notice something along this, the min and the max, they don't overlap. These two ranges here, they don't overlap. So you would know that a line could go right through the middle of those guys because they don't overlap. A line that is perpendicular to this particular axis. So you would basically use these ranges to find your minimum and maximum. And here, there is no edge. There's no edge you could pick, along these guys and find, like a line that would separate these two because they overlap everywhere. So, let's look and see what the code looks like, because, this is just kind of a visual of what it is. So let's, all right, so here's our polygon collision. So we have to loop over every edge in our first polygon and check to see, if basically what it's going to do is it's going to get the normal, and it's going to say, okay, here's our axis. This is the edge. So when you go back, let me go back to what I'm saying. So you've got this loop here, that's looping through every axis, every edge of the first polygon. So it's like basically, oh, that's a terrible line there, but it's basically going and, grabbing each edge one at a time, and it's trying to make that the axis, I mean, it's going to get the normal with that once we get into that overlap, but it's basically saying, okay, check every single edge here, and then we're going to go into the axis overlap that's on the polygon. That's our, get there. Yeah, all right. So the first thing we do when we take this axis, which is the edge that we picked out, is we're going to go through and we're going to look at the direction it's going. Because the axis has to be like a single, the axis has to be a vector. It can't be a line. And the way you do that is just getting the axis position and subtracting the end position. And you can do it the other way too. You could take the axis end position and subtract the position. It doesn't really matter. It's going to form the same, like which direction, no matter what, projecting along that's going to basically give you, it'll still work regardless. And then you normalize that, so you just set it to a value of 1, and then you rotate it 90 degrees. And rotating it 90 degrees is basically what's giving you these vector normals here. So you're basically grabbing each edge and rotating it 90 degrees, and you're trying to use that as a separating axis. So if you look at this guy here, this particular normal, you're not going to be able to use this normal as a separating axis, because when you project the values along, like projecting the values along there, you're going to see there's definitely overlap along this axis here. So the key is that there has to be overlap along every single one, because if there's overlap along every single one, then we know there is no line you could draw that's going to separate those two polygons. So, all right, so here we're rotating it 90 degrees, and then we're getting an axis range, So this is kind of where the magic happens, that we're boiling this down to a maximum and a minimum value along that axis when we're projecting, each of the edges. So we're going to project like every single edge for our first or for our second polygon along that vector, and then it's going to give us a maximum and minimum range. And then we're going to do the same thing for the polygon, this polygon, and that's going to give us a range along the axis for this particular polygon. And then we're going to have to check, are those two overlapping? And if they overlap, that means you cannot draw a line along that axis that separates those two polygons. So if there is overlap, you cannot separate them along that axis, but you have to check every single one. And as soon as you find one of these axes that you can use to separate it, as soon as you find it, then okay, there is no collision. So this is an example. You might test and test and test. You might be testing along this one. Okay, there's no separation there. There's no separation there. There's no separation there. And then as soon as you get to this one, oh, there's a separation. Well, it didn't matter that you tested all those other ones first. As soon as you find something that separates, you're good. You know that those two do not collide. So that's the basics. And then we covered projecting lines, in the previous one. So you're projecting this line along that direction, and that was basically, let me go back to the oriented rectangles. So that was basically this, this projection down here, this guy. That is, when you're projecting, you're basically trying, you've got, as I was saying, you have this axis, and you have these polygons that have all these various edges, here, and they have all these various edges here. And you're looking to see, okay, do those guys overlap along this axis? And the way you're doing is you're projecting, these edges with along 90-degree angles. Like you've got to find like a 90-degree angle between this point and that guy, and then you do the same thing here and you do the same thing here. So that's basically each point drawing a 90-degree angle, with it. Like, that's a little far out. You see, so the basically, for polygon 1, this is going to be your min, and this is going to be your max. And then for polygon 2, this is going to be your min, and this is going to be your max. And since those don't overlap, say, oh, well, they don't overlap, so clearly I should be able to draw, you know, a line that separates them right down the middle. You know, so if there is no overlap, that's when you know you can draw the line. So I covered the projection a little bit more in the oriented, when I covered oriented rectangles in part 2. You can look it up if you really want to dive into vector projection. But the basic idea is you have, you know, one vector and you have two vectors, and you're basically trying to find, you know, that 90-degree angle between this point and something along this vector line, and that creates a new vector. And that's these, you know, this is how you get the minimum maximum value, and that's basically what projection is. So there's kind of two scenarios. Like if you project this onto this vector, that, you know, you end up getting this point that's kind of part way, you know, up this vector here. But if you want to project this guy onto this smaller vector, you know, you've got to kind of continue the smaller vector, you know, as if he kept going, and then you draw this 90-degree angle here. So this, projecting this longer guy onto the shorter guy, creates a longer vector version of this one, you know, and that's basically how it's done. So let me just go and test this guy to show you how it's going, how it works. So, you know, we're doing the same sort of thing we've been doing forever, where I polygons. Oh, here's the other thing. I forgot to mention this, and it's really important. This only works for convex shapes, okay? So if you want a concave shape, you know, the first thing I did is I actually made, like, you know, a convex shape detector, which I should probably briefly go into. So the difference between, you know, a convex shape and a concave shape is basically whether, you know, any of the points along here, you know, kind of dip inward. So a concave shape would be something like, you know, would be something like this, you know. So it basically, when I was, I think, in grade school or middle school or something, they said, you know, think of it as forming a cave. So the separated axis theorem doesn't really work if you have any concavity, because, you know, you basically, when you get these concave shapes, it doesn't work. So the way you want to do it, if you really need concave shapes, I mean, there's a couple ways to do it. If you want to have like something that looks concave, but you think you could fudge it and people won't notice, you could take out, like, you know, you could basically have your collider, you know, smooth these pieces out, you know, so that, like, really your collider, if something kind of hits in this area where it's headed into the concave piece, you know, it's gonna blow up. And that's one simple way to do it, is have, you know, a collider that happens to be convex, even though your shape, you know, whatever your sprite is concave. Because, you know, for instance, the ship I was going to use in the asteroids game looks something like this, you know. So here's a concave piece right there. So it's jumping inside, and so if I shot something at it, I can't do a polygon test on that. So what I was going to do is basically just make this into a triangle, even though it's graphically displayed as this kind of like arrow looking thing. And that way, so say, you know, a little tiny asteroid gets in here, it's going to blow up as soon as it gets in there, even though, you know, who knows, maybe I could have accelerated away from it. But that's the solution I'm going to take. The other solution you could make is you could just break this into more than one polygons, you know, and do a compound collider. So you would say, okay, well, here's a convex polygon and here's a second convex polygon. They're both triangles. So I'll test this triangle and then I'll test this one. I'm not going to bother with that. But what I'm going to do in the game is I'm basically just going to make sure that everything is convex rather than allow for concave shapes. I mean, the one thing that's kind of nice is, with asteroids, a little bit of concavity kind of looks nice, but I just don't really want to write the code to basically look for and break these guys up. I've seen some of it online. It's doable. I don't really feel like it. But anyway, using the separated axis theorem, make sure that everything is convex. And you either do that through using, like if you have, like, say, a sprite, and you want to do a Polygon Collider on the sprite, and your sprite is some sort of spaceship, and it looks like this, and it's got these little things, and this is assuming that you're not doing pixel by pixel collision detection, which is slow. What I might eventually do is build some sort of tool where you could draw a polygon around this guy, and do polygon collision detection. So, if a bullet gets fired and it happens to hit you there, then odds are you would have been hit by it anyway, but you're probably going to see an explosion. I mean, I'd most likely do that over doing a compound collider, although you certainly can. There's nothing wrong with doing a compound collider, other than it just takes that much longer. So if you broke this guy into multiple polygons that were concave or convex rather, like say you broke it into 3 because you really wanted more precision, and this gets you a lot more precision, like doing something like this. Say you needed that, okay, well now you're using 3 times it's going to take 3 times the processing power to determine, if something collided with this. So anyway, it's easiest to stick to convex if you can. If not, there are ways around that, but I would recommend sticking with convex. But I think that is about all I need to show you guys on the separating axis theorem. Here's my test to make sure if something's convex. So if I remember right, yeah, I'm getting the normals, and then I'm getting the dot. So I'm taking the normal, of every edge, I think. Yeah, of every edge. I'm getting the normal of every edge, and I'm taking the dot product between that normal and the next edge. And basically, I want to determine, okay, are they all positive or are they all negative? So that the dot product is basically what I'm using, to determine if the dot product of the normal, a perpendicular vector to that edge. Basically, if the dot product is always of the same sign, then you're dealing with a convex shape, because that means the angle hasn't gone too far around in one from one edge to the other. Because if you look at a convex or a concave shape, anytime you have a concave shape, you'll have some big angular jump. So a convex shape won't have that. So like you have that angle, but then this is a really big one, and then smaller. So you're basically doing the normal thing and checking against the next one. You're basically looking at these angles and trying to figure out, okay, did one of them have this much larger angle than it's supposed to? Was it larger than 90 degrees? And if that's the case, then you ended up with a convex shape. So that's how I tested for it. I don't think most of the time you need that, but I think that should cover about everything with the separating axis theorem, and Polygon on Polygon Collision. So yeah, I think that is it, and I hope you liked it. Please let me know if you have any questions. If there's something I didn't cover, if I covered too much. I'm still fairly new to this tutorial thing, so just trying to get into it. And please subscribe if you get the chance. Thank you very much.